Yes. So Maxime, yes, the co-limit is being computed over delta op, but the point is that the opposite of the simplex category is cofinal in the appropriate. I'm sweeping some details under the rug here, but essentially you can compute the value, you can compute the co-limit of this cyclic object essentially as the co-limit of the underlying simplicial object. And isn't co-limit over lambda the homotopy orbits? Right, so Noah, I'm not exactly sure what are you saying that are you saying that lambda is sort of the quotient of the epicyclic category? Is that what you're saying, or maybe not the epicyclic? Yeah, the epicyclic category.
Sorry, can I speak in here instead of typing? It might be better.
Yeah, go ahead, Noah. Yeah.
So I guess first of all, this limit, are you taking it sort of at the one categorical or infinity category level?
This is happening at the level of infinity categories.
Okay, so isn't the functor itself the thing with S1 action, and then when you take the co-limit, you're taking the co-limit over BT?
So if I'm recalling correctly, what ends up happening is you have functors from lambda to spectra, say, but then what you end up doing is you know that lambda is I believe this is going to be a quotient out by I want to say BZ, and so this ends up being equivalent to functors, BZ equivariant functors from lambda infinity to spectra, and then the map from lambda op into lambda infinity is cofinal. And so what you end up getting is when you take this co-limit, you're going to end up essentially in the point that I mean to say is essentially that this co-limit functor here lands in spectra with S1 action. Does that address what you're concerned about at all, Noah?
I'll have to think about it, but we can move on.
Right. Yeah. So I'm sorry for doing a shoddy job of explaining this, but the technical details are in Appendix B of Nicolas Schulze for the interested participants. And it's possible I could be saying things that are technically incorrect, but it's the key point is that if you take the geometric realization of a cyclic object, you get something with an S1 action. Okay, so right, so THHA admits an S1 action, and it actually has more structure. It has the structure of something called this is a cyclotomic spectrum. But I don't want to say really anything about this because I think this would sort of be we would quickly run out of time, as we're sort of already quickly running out of time. But essentially the thing to mention is that one uses the cyclotomic structure on THHA to define TC of A. And I don't want to say too much more. Well, maybe what I will say is TC of A is the mapping spectrum in cyclotomic spectra from a certain cyclotomic spectrum to the THH of A. And I don't want to say any more than this because it would sort of take too long. Okay, so right, so maybe are there other questions people have at this juncture that I can answer? Okay, all right. So let's do a couple of examples because these are sort of important to keep in mind. So there are kind of as far as I know, there are sort of, well, let me just write some examples down. So the first thing is if we want to calculate the THH of HFP, so the homotopy groups of this thing are isomorphic to the polynomial algebra FP adjoin a generator in degree 2, and this is due to Bookstedt originally, but there is a very slick proof of this fact, which you can deduce by using some work of Bloomberg, Cohen, Schlicht-Kroll, and Tom spectra, which I will mention something about again in a minute. Another calculation is so THH of the integers is a generalized Eilenberg-MacLane spectrum with, let's see, let's hope I don't screw up my indexing here, pi k of THH of z is equal to z when k is 0. It's equal to z mod n when k is equal to 2n minus 1 and then 0 otherwise. And then finally 3, so we also know how to calculate THH of perfectoid rings. Well, maybe I'll say P complete THH just to be a bit careful. And the story here is analogous to the computation due to Bockstedt up here. And additionally, we also know how to compute the THH of Tom spectra. And I suppose I should also add this is a result due to Abat, Morrow, and Schulze. And then the THH of Tom spectra is due to so the computation of THHZ is also due to Bookstedt originally, and then the THH of Tom spectra is due to Bloomberg, Cohen. Let's hope I don't screw this up. Schlicht. Schlicht-Kroll. Okay, and so there's also so this is sort of a large host of examples where we know how to compute topological Hochschild homology, and there's a lot of really interesting deep mathematics that's happening in this picture, as you may be aware of, and it turns out that the computation of THH of HFP and in general the means for calculating THH of Tom spectra are really related to a bunch of cohomology operations and the structure of the C-mod algebra. And so this is really deeply connected to understanding a lot of things in stable homotopy theory, which is quite cool. Okay, and I'm utterly ill-equipped to say more about that than I have. Okay. So, right. So now what I want to do is I want to shift focus a little bit, or maybe so just to recap, we have these invariants THH and TC, and they're supposed to be certain kinds of approximations of algebraic K theory, and in good cases we can say something about how K theory is related to these invariants. And so something that is worth noting is that algebraic K theory has a really nice property that it satisfies what is called Zariski descent. And what that means essentially is, for example, an affine scheme and I want to understand what the K-theory of this, maybe the right way to say it is if I have a commutative ring and I want to understand the algebraic K-theory spectrum of this commutative ring, I can look at a family of principal open subs covering the spectrum of this affine scheme, and then I can ask what the K-theory of each of these principal opens is. And descent is essentially just a way of saying I can recover the value of K-theory on my original ring by looking at K-theory of these principal opens or of these localizations of my ring. And so this descent type business is essentially a fancy way of saying, can I take a problem that I'm interested in studying and break it apart into maybe more manageable pieces? And then can I recover the invariance I'm interested in by looking at sort of specific types of covers or specific types of open subsets of my objects? And so I'll say a bit more about this later, but I just want to state a theorem right now, which is due to Bott-Morrell-Schulze, which I'm just going to abbreviate BMS2. I think this is maybe poor form since I should probably write out all their names, but their names are somewhat long when squished together. So THH, topological Hochschild homology, has what's called faithfully flat descent for discrete, well, maybe just for commutative rings. And what do I mean by this? All I mean is that if I take a map of rings A to B, and this is faithfully flat, I can consider the diagram that I can consider the following cosimplicial diagram. This is the Kobar complex or the Czech conurve sometimes. And what I can do is I can hit this cosimplicial diagram with THH. And then to say that I have a faithfully flat descent is just to say that when I look at the natural map from THHA to the inverse limit over this cosimplicial diagram, this is an equivalence. And so this is essentially saying that you know, I can sort of take, I can calculate the value of THH of A by looking at the value of THH on all of these iterates of taking the tensor product. And so that's what faithfully flat descent means. And so I want to state the following theorem, which is that THH has faithfully flat descent for connective E infinity ring spectra. So what this means in this context is just that there is a suitable notion of being faithfully flat for E infinity ring spectra, and whenever I have such a map, I can form the same type of Kobar complex and consider exactly this limit condition. And so it's precisely the same thing, except that the tensor product of discrete rings is replaced with the smash product of E infinity ring spectra in this case. So this is the theorem that I want to take some time to try to, well, first I'm going to talk about some of the techniques that go into proving this theorem and talk about filtered spectra and Whitehead towers and things of this nature, and then hopefully there will be like some amount of time to comment on how the proof of this thing goes, and how one can sort of use this result from BMS2 to bootstrap up to the case of connective E infinity ring spectra. And so this is what I would like to do with the rest of the time. Okay, so that was a long introduction segment. Okay, so setup of definitions. Okay. So maybe this is a good time to pause and see if there are other questions from the audience. So question, do faithfully flat covers of connected B-infinity ring spectra form covering families of some growth unique topology as in the discrete case? Yes, absolutely. And so really there's some, so secretly what I mean when I'm saying it has faithfully flat descent is that it is a sheaf for the FPQC topology on E-infinity ring spectra. And there's a lemma similar to the lemma in the case of ordinary categories that, you know, you're a sheaf if you, preserve these sort of, you know, standard coverings and then also preserve products or whatever. And so I'm sweeping that under the rug. But yes, yeah. And so in particular, the covering sieves are just finite finite collections of maps. So whenever I take the product of the codomains, the map from one ring to the product of the other ones is faithfully flat. And so those are the generators of the covering families for that topology. Okay. All right. So in that case, so what I first want to talk about is the May filtration on THH, because I think this is a really interesting. Object, and I hope. Well, I mean, I just want to advertise that this is a really nice filtration for THH, and there's an associated spectral sequence which is useful, and I'll mention some of this. Yeah.
I have a small question.
Yes.
Can you remind, does algebraic K theory satisfy some sort of flat descent?
Sorry?
Does algebraic K theory satisfy some kind of flat descent?
Algebraic K theory does not satisfy flat descent. In fact, it doesn't even satisfy étale descent. It has Nisnevich descent, but that is about it.
Yeah, just for guess. Thank you.
Yes. Yep. Yeah. Mm-hmm. Yeah. So yeah, that's worth pointing out. Is that so one of the bad things about K theory is that it doesn't have, say, étale descent or other useful forms of descent, but the other invariants which approximate it are more well behaved in this respect. And so, from a sort of big picture point of view, the hope would be that one could use these descent type properties to do some more types of calculations of THH and TC, and then maybe say something about K theory as a consequence of that. But this is sort of, in practice, this is quite challenging. Okay, so I want to say something about the May filtration on THH. And the first thing that I want to say is that, so the cyclic bar construction sort of wasn't that special to algebra spectra at all. So in particular, one can run various other types of cyclic bar constructions in suitably nice symmetric monoidal categories. So as long as you have an E1 algebra object, you can form a type of cyclic bar construction and take a resolution, and take the colimit of this big diagram, and you can get some analog of topological Hochschild homology. But now you're going to be working in another type of category, and so maybe I'll just finish writing isn't special to spectra. And in particular, the way that we're going to set up the May filtration on THH is by, instead of performing the cyclic bar construction with respect to the smash product, we're going to perform the cyclic bar construction with respect to the day convolution of n filtered algebras. And so what that's essentially going to look like is, I'm going to have some kind of filtered algebra A, and then I'm going to have some big cyclic bar construction, but this is going to be the day convolution product, which I'll remind everyone of in a moment. And essentially the point is that when we form this object and we pass to the colimit, there are a variety of functors that there are a bunch of functors which essentially relate n-filtered spectra back to spectra, and you have to check the compatibility of these functors with this procedure of forming this sort of filtered bar construction. But once you do that, this will essentially tell you a lot of useful things that you will want to know. So for example, like in this case, if I sort of take the if I take the zeroth term in this in the resulting filtered spectrum that I get by taking the geometric realization here, this will be THH of the zeroth part of the filtered spectrum that we fed into this analog of the cyclic bar construction. And I'll make this a bit more explicit in a moment. But let's just write some definitions down now so we can make a bit more sense of all this. So I'm going to define a category called tau spectra, which is going to be functors from ZOP greater than or equal to 0 into my category of spectra. And so here I am giving this sort of the usual poset ordering. And this is the category of towers of spectra, or maybe more something which is slightly more true is that this is the category of n filtered spectra. So an object in this category is just a functor from ZOP greater than or equal to 0 into spectra, which we can just sort of read off as a tower of spectra that looks like this. And so these are the ones that sort of stop at the 0th term. And so what we can do is we can essentially view this tower as some kind of descending filtration and I'm going to put quotes around this of x0. Okay. So we can sort of view x1 and x2 and so on and so forth as better and better and better approximations of the 0th term. And so now I have to say some things that are true about this category that we're going to use. Okay, so some properties. So the first thing to say is that the n-filtered spectra is a nice category. So in particular, it's presentable and stable. So it has a good notion of cofiber sequences. It has a zero object. You have sort of a reasonably nice set of generators, which which every object is a big colimit of. And so this is a nice category. It's well behaved. Two is that so n-filtered spectra is symmetric monoidal. With the following product. So if I take two n-filtered spectra x and y, the formula for their day convolution, so the nth level is going to be the colimit of this diagram here. So, and of course, this is taken over the sphere spectrum, and so this becomes symmetric monoidal for this day convolution product. And what you can also say is that this symmetric monoidal product is going to preserve colimits separately in each variable, which is a consequence of the fact that this happens for the smash product of spectra. Okay, and also maybe I'll just say that the unit for this for the symmetric monoidal structure is the tower, which is just s in degree 0 and then 0 elsewhere. So this is the unit. Okay, and so now maybe, what do I want to say? So a couple more things. So there's a functor, maybe the associated graded, which goes from towers of spectra down to spectra, which is given by we take an n-filtered spectrum and then we send it to the direct sum over all of the cofibers of all the maps in our tower. And so this is the associated graded spectrum. And so this functor is quite nice. This is actually symmetric monoidal. So there is another functor from towers of spectra to spectra, which is given by evaluation at 0. So I take my n-filtered spectrum and I just spit out the 0th term in that. And this is also a symmetric monoidal functor. And then 5, so there exists a Whitehead tower functor which goes from spectra to n-filtered spectra, which on objects is given by taking x to the tower naturally associated to all of these co-truncations of x. And this functor is lax monoidal. And I should mention that these functors are all symmetric monoidal or lax monoidal with respect to the day convolution on towers, and then the smash product on spectra. Okay, and so something that is worth pointing out is that in the case when x is a connective spectrum, we know that the 0th term in its associated Whitehead tower is just the same as x. So this is kind of important, and this is something that we will have to use when we're talking about the May filtration and why part of the reason why some of this works. There is essentially the case of n-filtered spectra, right, is sort of supposed to handle the case of connective things, because if you had something possibly non-connective, what you could do is you could sort of let the co-truncations run off in the negative direction as well. And then you would view this big, there you would be indexing a diagram by all of the integers. And you would think about this whole thing as a filtration on the co-limit of this big thing. Because what you're essentially doing is by decreasing the degree, you are sort of allowing more and more homotopy groups to possibly appear in smaller degrees. But this situation is just suited to handling connective things. Okay, so this is sort of irritating and technical, and so why did I spend a lot of time talking about this stuff? Well, the main payoff of this thing is that all of these functors induce functors on E1 algebras or even E infinity algebras. And so because these things are suitably lax monoidal. And so in particular, we have a Whitehead tower functor. So this category here, this is going to be the category of E1 algebras in n-filtered spectra. And I'm going to denote this thing by alg tau for brevity. And I'm also going to denote this thing here just by alg for brevity. And so what you can, so this here is essentially, this alg tau thing is really just sort of filtered E1 algebras. You know, there is the point is that the 0th term in your filtered algebra is going to be an E1 algebra in its own right, and then sort of there are going to be suitably compatible multiplication maps from all of the different layers to so for example from the ith term and the jth term into the ith plus jth term. So we're going to get some suitable Whitehead tower functor. We're going to get some suitable evaluation functor. Call this thing W, and then we're going to get some suitable associated graded functor. Okay, and so now we're in the right position to make the following definition. So for an n-filtered algebra spectrum, you know, maybe we could say the n-filtered THH of A is the co-limit of the cyclic bar construction. with respect to the day convolution. So we take the colimit over this big diagram. And this is going to be, I'm going to denote this by THH tau of A, like that. And so this is going to be, this is an object in alg tau itself. And in fact, sorry, not an object in alg tau, I've misspoken, in tau spectra. So this is going to be an object in towers of spectra, and in fact, essentially by similar considerations that we made earlier when just talking about ordinary THH, this is going to have an S1 action, and there is going to be, there's also a suitable sort of filtered cyclotomic action as well, or sorry, filtered cyclotomic structure that appears, but a discussion of this is somewhat irritating, and I'd rather avoid this. But there are ways to give this a filtered cyclotomic type structure, which in this case can also give you another type of, can give you some sort of filtered type of topological cyclic homology as well. Okay, and so essentially the point is that when I, so let's say I fix an E1 algebra spectrum, then if I take the Whitehead, let's just say connective, if I take the Whitehead tower of A, the point is that now if I take if I do THH, this n-filtered THH, this is going to be some sort of filtered spectrum. And it turns out that if you look at the 0th term here, this is actually just equivalent to THH of A0. And so what you're getting is that in the case where you start just with an E1 algebra spectrum, you're actually getting some sort of n-filtered object, which is sort of approximating THH of the original algebra that you started out with. Sorry, I've written a little subscript there that didn't need to be there. Okay, and so essentially the utility of this is that in practical terms, there's a spectral sequence associated to this filtration, and the spectral sequence looks something like the following. So the E2 term is going to look like pi star of THH of actually H of pi star of A, and it's going to converge to pi star of THH of A. Okay, and so, right, so I'm running a bit low on time, so I will try to move a little bit more quickly.
On the left-hand side of a spectral sequence, you consider like graded THH of a graded algebra, of a graded.
Yes, yeah.
Mm-hmm. Okay, fine.
Yeah, so there are, maybe to elaborate on this comment a bit more, the key point is that one of the, so maybe I'll just, some key properties of this filtration is essentially that one, if I take the associated graded of I'm going to get THH of the associated graded of this filtered spectrum here. And then the other thing is that as we sort of saw earlier, the 0th term in this of this filtered thing is just going to be the same thing as THH of A0. Where here in both cases we're just feeding in any old n-filtered algebra spectrum. Okay, and so, right, so, all right, let me quickly skip through a bit of material and try to say something about how this is going to be helpful for us. Okay, so, sorry, are there other questions about this May filtration or this filtration on THH today for connected algebras. Right. So by reindexing, can you get all of these results for bounded below spectra, or is there something important about connective? Right. So right, by reindexing, you can do all of this stuff with things that are bounded below. So I would imagine that by reindexing, you can do this, and it should be okay. I am hesitant to say something super definitive because I haven't thought through it carefully. But essentially, right, the point is that in the case where you, yeah, it should work for bounded below things. It shouldn't be a problem. But unfortunately, you know, one would prefer to work with you know, sort of these unbounded filtrations, because they're going to, in practice, they're going to capture the whole Whitehead tower of some possibly non-connective algebra spectrum. And there are ways to do this, and you can essentially prove analogs of the results that I have written down here in this case, except you replace the evaluation at zero functor with the co-limit functor. And the thing about THH is that it's nice and compatible with co-limits in a good way, that it allows you to identify the co-limit of this now Z-filtered thing with the THH of the co-limit of the Z-index diagram that you're now working with. Okay, so let's see. So essentially, the main application of this filtration on THH is to sort of bootstrap the result from Bott-Morrow-Schulze that I wrote down earlier. And so what I want to do now is I just want to give a very, very, very rough outline of how this type of argument goes. So essentially, now that we've established a lot of good properties of this May filtration, let's try to see how this goes. So right, so if we, so we know the case of discrete rings. Right, so what we'd like to do is we would like to sort of bootstrap this up. And so the bootstrapping sort of proceeds as follows. So you start with this case, and then you combine the BMS2 result with a theorem due to Bjorn Dundas and John Rogness, which has to do with something called one connected descent, which I can maybe say something about when there are further questions, but I'm sort of running low on time. So you combine this with the BMS2 result with the theorem of Dundas-Rogness to deduce the theorem for generalized Eilenberg-MacLane spectra. Okay, and so now once we know the result here, what we can do is we know that the associated graded of THH of the Whitehead tower of some connective V infinity ring spectrum is going to be equivalent to the THH of the generalized Eilenberg-MacLane spectrum associated to A, because that is precisely the associated graded of the Whitehead tower. And so in particular, by essentially saying a bunch of equivalences, what we can deduce is we can deduce that we have descent for the sort of associated graded object given coming from this n-filtered analog of THH. And then what we can do is we can bootstrap this up since we have control over the associated graded, we are suitably able to get control over all of the sort of all of the terms in a tower which approximates THH of A, and whose terms are exactly controlled by this associated graded. And so we can sort of do induction up a tower to get the result for THH.
Sorry, could you remind the definition of a faithfully flat homomorphism in the case of E-infinity ring spectrum?
Yes, yeah, absolutely. So a faithfully flat map is just going to be some map A to B with the two following properties. One, let's call this F. So pi 0 of F is faithfully flat itself, and then 2, you have an isomorphism of graded rings.
Makes sense. Yeah.
Yes. Yeah. Right.
This is exactly what I expect.
Yes. Yeah. Precisely. Yeah. So this has to be an isomorphism. Right. So right. So I think I am just about out of time. So I will stop talking now. Thank you all for your attention. And I'd be happy to answer any questions people have about this stuff.
So I'll go ahead and unmute everyone first so we can thank Liam. Okay.
I have a question.
Yeah. What's up?
So first of all, sorry I missed the first part of your talk, but it was a very good talk, the parts I did see. So I'm sorry if you already mentioned this, but did you do any computations with this result?
No. So I have not. I will be the first to admit that sort of this technical improvement to this result, the main consequence, this faithfully flat descent business, is really sort of just a kind of nice technical improvement of the BMS2 result. And so what I have tried to think about a little bit is examples of where we might be wanting to do some types of calculations of this flavor. But unfortunately, the problem is that most of the nice examples that we have floating around in the literature are oftentimes non-connective spectra. And it's also sort of a bit unclear to me if there is a reasonable sort of family of examples that exists out there that are sort of not discrete, and basically because I should also mention that that THH, while it is a sheaf for the FPQC topology on connective E-infinity ring spectra, the more practical type of descent result that one typically works with is étale base change. And this étale base change holds not only for E-infinity ring spectra, but for it holds for non-connective E2 rings even. And this is a theorem due to Akil Matthew and Dustin Clausen. Originally, the case of E-infinity ring spectra, possibly non-connective, is originally due to Akil, but they have an improvement in a recent paper of theirs on étale K-theory and hyperdescent. So in practice, one typically works with étale base change as opposed to this faithfully flat kind of stuff. But I would be really interested to know if there are sort of good examples where one could apply this type of stuff, because I'm sort of I couldn't think of any really obvious applications of this theorem. Yeah.
Actually, this connects into my previous question too. Is there any place you essentially use connective instead of just bounded below? I mean, I know you skipped over the beef with the proof there, but.
So right. Here's what I am. What I would imagine is the case is that you can prove a lot of things about. You could run the exact same arguments, except the Whitehead tower truncation functors would be sort of going a degree lower than 0, and so you would be working with you would be able to do stuff for bounded below a fixed degree, but I am unsure as to how all of the types of degree shiftings would sort of piece together after you've sort of proved all of these theorems for proved all that all these constructions go through for a bounded below a fixed degree. I'm not exactly sure, and I'd be really interested to maybe think about this and talk about this later. Yeah,
This could be an interesting source of examples. Thanks.
yes,
That was
yeah,
good
yeah,
talk.
most definitely. Yeah.
Any other questions?
Can you show again the sequence before?
Sorry, can you say that again? I didn't.
Can you show again with spectral sequence which you take?
Yes, yeah. So this is this is called the THH-May spectral sequence.
I mean, it looks like if you substitute there a sphere spectrum, you will get something very interesting.
Yes, yeah, absolutely. You definitely will. I mean, you will get something. You will be converging to the sphere spectrum, and you'll sort of have as absolutely. I'm actually not sure. So the main reference for this spectral sequence or spectral sequence of this type are going to be found in a paper of Engelveit on Witt vectors of finite length. And then also in the recent paper of Angelini Knoll and Salch and they precisely handle the case of this THH May spectral sequence, and they do some interesting chromatic calculations with it. So I don't know if anybody has seriously thought about the spectral sequence you get just by plugging in the sphere spectrum, but that's certainly very interesting.
You get a lot of differentials, what could be.
Yes, yeah, absolutely. Absolutely.
Yeah, nice, thank you.
Yeah, that's a great question. Thanks.
Yep, and with that, let's all thank Liam one more time.